Okay, this is one of my concepts of time travel, either forward in time or backwards in time, using a large planet or a large sun of any galaxy. We know that there's a lot of planets in the universe, or a lot of suns. They have larger in size, and they warp time and space. Just like your typical bed sheet in your house, in your bed, if you have a whole bunch of marbles, the marbles will dent the bottom of the sheet, and that's what happens in real life with our planets, our suns, and our moons, and everything that spins around the universe, our galaxies. Uh, Everything dents the fabric itself, which is right here. It's like a bed sheet. So even the Earth itself, even the moon, warps the bottom of the time and space, which is, like I said, the comparison is almost the same as your typical bed sheet. Uh, but anyway, the concept here for time travel is very simple. Example number one. Here we have a spacecraft, and it's going to go along a straight line to reach this point. We're going to use numbers for example purposes, and that's all going to be for example purposes. But anyway, since it's a straight line going with the same flat surface of time and space right here, it's going to go straight forward and straight line. It's not going to deviate. It's going to be a straight line. So this spacecraft going straight forward in a straight line, it'll take them 24 hours for example purposes, 24 hours. So let's say this spacecraft takes off from here on Monday, and next day he gets there on Tuesday. So it took him 24 hours to get there, because let's say this object, a planet or a sun, is massive, massive, massive. It might have been going maybe 5 miles an hour, the spacecraft, from point A to point B. Let's say it took him 24 hours to get there, one whole day. So it took off on Monday, and from point A to point B, and got there Tuesday. So 24 hours later, one day. That's how long it took for this spacecraft. Now, example number two. The other spacecraft is going to go along the curvature on the bottom of the time and space and go reach the same point. But in this case, this spacecraft is going to follow the same curvature as time and space, so underneath the planet or sun of a massive star. So it's going to go along the fabric of time and space, and instead of going straight forward, it's going to go curved downward toward the bottom of the planet, and then go this way. So basically, it's going to follow the curvature of the fabric of time and space, the curvature that the actual planet is making while it's on top of the fabric of time and space. So it's going to follow the same curvature on the bottom, and it takes off on Monday, and traveling at 5 miles an hour, let's say, because the massive planet is going to follow the curvature, and it's going to take it twice as long. So it's going to reach from point A to point B. Let's say it takes them 24 hours. Plus 24 hours, let's say it's going to take them 48 hours total, 2 days. So let's say this spacecraft takes off on Monday, and it takes them 48 hours. So 2 days later, it gets to its final destination on Wednesday. So it took twice as long as the other one, for example purposes. So because the curvature, it takes a longer route. When you travel a straight line, it's a lot quicker than a detour. But in this case, the second example took the curvature of the time and space of the planet underneath, and it's a detour, it's a curve, so it takes longer than a straight line. So basically, this spacecraft, when it reached this point, it's 1 day into the future. Okay, right here. So because the first example, the spacecraft took 24 hours, 1 day in a straight line. Second example, the second spacecraft followed a different route underneath the planet, the curvature of the planet that's made by the planet itself on the fabric of time. It took them 2 days, and it reached to this point on Wednesday. So the first example reaches the destination on Tuesday. The second example that follow the curvature reach its destination on Wednesday, 48 hours later, which is 2 days. So it time traveled 1 day forward in time. Because its destination was slower because of the curvature. Not only was slower, it took longer to get to point A to point B. So it traveled in time 1 day extra, basically 48 hours. Because normally it would have taken 1 day plus 1 day of curvature extra. The route was longer, so it took 48 hours, 2 days extra. So it basically arrived on Wednesday. So it time traveled forward in time 1 day. So because it followed the longer route going this way. So now this example, the second example, because it took a longer route and it took longer, basically slowed down, it time travel forward 24 hours into the future. In real life, it could be seconds or milliseconds, even minutes into the future, depending on the massive planet or sun or star, or even our own sun could do this easily. Even Earth can actually do milliseconds in this concept. That's traveling forward. Now, traveling backwards, it's also very, very possible. Here I have a spacecraft doing a same level straight line, but instead of going straight, this spacecraft is going around the sun or a large planet like Jupiter, but the same level as a plane of time and space on a same straight line. So it's going around the planet on a straight line. Now the circumference of this rotation around a circle around the massive planet like Sun or Jupiter or a large planet, it's a same level plane field straight line. So this is the circumference is larger. Now here we have another object on the bottom rotating right here. Circumference is smaller. Here we have a third object, a spacecraft rotating in a circumference smaller. So basically this one right here, let's say it goes around the massive object or planet or star or sun. Let's say, for example purposes, it takes them 2 days or 48 hours to make a complete circle around the sun or a large planet or star. So it takes them 48 hours at 5 miles an hour around the whole planet. Let's say it takes them 48 hours or 2 days. Okay, because the circumference is larger. But now we have this object, or in this object right here, either one. But let's take this one for example. Now this object right here takes them, let's say, because the circumference is smaller, it's going to take them less time to go around and make a complete circle. Okay, but the third one, let's say, for example, underneath the object, let's say it's so small, the rotation around it to go around, make a circumference, complete circumference, circle, or around the bottom of the planet, large planet. Let's say it takes them 24 hours, or basically 1 full day to complete a circle. So this object, because it's actually, for example purposes, let's say this object starts at one point of the circle, it makes a whole rotation, it takes them 24 hours, 1 day. Let's say it took off on Monday here, okay, took off on Monday, and to make a complete circle, got there on Tuesday. So that's 24 hours, okay. Let's say the other object on top takes off from this point, makes a complete circle, 24 hours. That's 2 days. So this object right here will actually travel backwards in time, because this is the same playing field as everybody else, and it took 2 day rotation, which is normal time and space, even space coming in. But this spacecraft is making a quicker rotation, and it takes 1 day. So by the time it's 1 day, let's say, it gets to point A, starts on Monday and gets there on Tuesday. So this is gets there on Tuesday, and this object here starts on Monday and gets there on Wednesday. So it starts on Monday, 2 days later it gets there on Wednesday. That's 48 hours, and this is only took 24 hours. So this spacecraft making rotations along the fabric of time and space, the curvature, doing a complete circle, it took 1 day less. So this object will time travel backwards 1 day, because time and space will run this way, its course, and let's say the velocity of the time and space in this case scenario, it's flowing at the same speed as the same level here, same spinning up here of this rotation. So this took 2 days to travel one circle, which is to complete time and space around everybody else, but this one took 1 day to make one rotation along the curvature of time and space. So this object traveled backwards 1 day in time. Remember, it's just it's all depends on the curvature of time and space. Same thing happens in a black hole. Black holes have a massive curvature and affects time and space, because it takes longer for the light to reach from point A. Well, in this case, black holes eat the light, but even the curvature of a large planet, it bends the light. So it takes a light, when it goes straight forward, it takes no time to reach the other side. But the curvature actually is a longer route. It takes a longer time to reach the light on the other side. So basically, any time you have curvature, it takes longer to reach from point A to point B, because straight line is always the quickest way to travel. So that's time travel on both purposes. The first example, straight line, and follow the curvature underneath the planet, that's traveling forward in time. And then the second example, where this rotation is equal the same as the flat of time and space, the average time and space for everybody in space, but you underneath here, you're following the curvature, but you're making a complete circle 1 day less, and then you're traveling backward in time. Now, how can it be useful or for our daily life? We know that Elon Musk is putting satellites, 30,000, I don't know how the exact number, tens of thousands of satellites around the entire Earth itself and a rotation. But if you think about it, any satellites in this area compared to the satellites above here, so it'd be about, maybe because the planet is not so large, but it still bends time and space. Satellites flowing this way will actually be able be in a milliseconds behind in time. And this right here would be actual time itself. So satellites going this way in milliseconds will be backward in time, or in this case will be actually time itself, a normal time space. Also, satellites, if they were in my concept, if they had the satellites were actually going this way down, or spacecraft and back. So if you had the spacecraft going this way and this way, making U-turns and going this way, and then make a U-turn and go this way, make a U-turn and go this way, make a U-turn, instead of going a straight line. So you have a spacecraft or satellite going making a U-turn underneath the planet. So what that happens is that spacecraft, like I said, straight line is quicker. It's normal time everybody goes by. But if you go underneath the planet, it's a longer route. And it's, in this case example, takes twice as long. So if you have a satellite or a spacecraft going this way, making a U-turn, what happens is that spacecraft is going forward in time, because everything's running a normal pace, but everything going here takes a longer route, it's going slower. So everything passes by. So the time, like I explained earlier, anybody doing this U-turn, kind of like following the time, the fabric of time and space, making a U-turn, will slow down because it's a longer distance. So it'll take longer from point A to point B. So basically, be actually traveling forward in time. So if you got satellites doing that, or let's say satellites, then I think they would actually they might see future events by milliseconds, because, like I said, the Earth is not a very large planet, but it's still dense, time and space itself. But if it's massive enough, like the sun, then that actually will affect a larger time and space forward. So depending on how large this is, that's the more effective time dilation that actually would occur. So this is the concept basically that you could use in satellites, you could use for travel, you could use for time travel. Basically, if you go straight forward, normal time, you follow underneath the curvature, you go back in time. So if a spacecraft is rotating on the bottom, then it actually moves quicker in time. So actually, in theory, it goes back in time. So if you travel point A, for example, the first one, if you travel along the curvature, or you go back, like I said, you turn and go back this way, or just go once or a couple times. If you follow this curvature going this way, you're going to travel forward in time. But if you go this rotation right here, basically you're traveling forward. Oh, I'm sorry, traveling into the past. So I guess the more I can explain it real quick. Curvature, forward in time. This way, backward in time. Hope you guys get the concept. Like I said, it's a cool idea. We're just following the same curvature of the Earth or planets or sun or stars make to travel in time, either forward or backwards. Forward is basically along the curvature. If you rotate here, which is smaller rotations instead of the even line here, then you travel back in time. Like I said, it could be milliseconds, minutes, or longer, either forward in time or backward in time, depending on the size of this object or star or planet or sun. It's a pretty cool idea. Anyway, you guys have a good one. Megatron Inventors.